Now, next result is let n and n dash be a normed space if dimension of n dash, this is n dash, is less than infinity, then T is a compact linear operator. Now, this is basically corollary of the previous theorem. Since the dimension of n dash is less than infinity, that is given, it implies T n to n dash, which is a bounded linear operator. Also, we know that dimension of Tn, which is less than equal to dimension of n dash, so this is again less than infinity. Then by previous result that we discussed in the previous lecture, T is a compact operator. So that is our result. We already did this theorem, and after this theorem, we proved that we proved that this theorem is applicable only uniform convergent operator. This result is not applicable for a strongly convergent operators. Now, in order to contradict that result, consider a example that we will discuss in this remark. Now, the above theorem that we discussed in the previous lecture applicable for uniform convergence operator, not for strongly convergent operator. So in this case, consider an example, consider Tn operator from small l squared to small n squared. It is defined by, now L square consisting a sequence x1, x2, x3, xn and so on. Now we take the operator in such a way that nth term are non-zero and after nth term other terms are 0. For example, if it is a t1x, then operator is x1 0 0 0 and so on. If it is a t2x, in that case this is a x1 x2 and other terms are 0. Similarly, for tnx, x1 x2 up to nth term, it is a non-zero and other terms are 0, where x is equal to xi belongs to L square. So L square consisting a sequence. This operator is a linear, it is clearly and bounded operator. It implies because it is infinite dimensional. Now this is a Tn is a compact linear operator. Now it is a compact linear operator. Now clearly Tnx, when n approaches to identity, then this operator become the identity operator. When n approaches to infinity, in that case, the Tn operator act as identity, right? So it means Tnx approaches to x when n approaches to infinity. So it means it behave as the Ix. It behave as the Ix. It means this operator is strongly convergent to I. This operator is strongly convergent to I. If this is strongly convergent to I, but I is not a compact. Why I is not compact? Because dimension of L square is infinity. If dimension of L square is infinity, so we already proved in previous result, part C, if dimension of n is infinity, in that case I is not a compact operator. Clear? So in this means this sequence is strongly convergent to I, but this is not a compact operator. So limit is not a compact operator. So in this way we can prove that this theorem is applicable only for the uniform convergent operator, not for a strongly convergent operator. So this operator that we define, it is a linear transformation as well as a bounded, right? So this is linear transformation and bounded. Now that's why it is a compact. If it is a compact, when n approaches to infinity, Tn is strongly convergent to I, but dimension of L square is infinity. So I is not compact. So that prove our result. Now next is again that very important result. Let n and n dash be a normed space and T and n dash a compact linear operator that is given. Suppose this sequence xn, which is weakly convergent to x, where xn belongs to n, right? That it belongs to this space. Now, first, remind the definition of weakly convergent. So, what is weakly convergent? If this sequence approaches to x, then its f image is also approaches to f image of x. Clear? So that is definition of weakly convergent. Our purpose is to prove that the image of this txn, so that is in n dash, that is strongly convergent to y. So yn, its image is strongly convergent to its image, right? So if it is a weakly convergent, then its image and its image, they are strongly convergent to each other. Now let yn, which is equal to txn, xn belongs to n and y belongs to tx. That is given. Now given xn is weakly convergent to x and our purpose is yn is strongly convergent to y. So what is the definition of strongly convergent? Norm of yn minus y approaches to 0 as n approaches to infinity. Now suppose in order to prove by contradiction, suppose this yn does not strongly converge to y. It means this condition is not applicable. Equation number 2 is not applicable. Yeah, it does not hold. If it does not hold, then it means norm of this does not approaches to 0 as n approaches to infinity, right? It means yn has subsequence ynk which satisfy this condition greater than 0, and it implies it is greater than epsilon for some epsilon greater than 0. Since this xn is weakly convergent to x, then it implies xn is a bounded. So that is a result of weakly convergent. Now in this case, T from n to n dash, it is a compact linear operator. By definition of compact linear operator, if we have some bounded sequence in n, as xn is bounded sequence in n, then its image has convergent subsequence. That is a definition of compact linear operator. Now, since xn is bounded sequence in n, then its image is has convergent subsequence in n dash. That is definition of compact linear operator, right? So in this way, by using this definition, Txn has convergent subsequence. Suppose we can say that yk bar, right? Txnk, we can say that. It means it converges to y bar. It converges to y bar. Clear? Now, this converges to y bar. If it is convergent and yk bar, this is again convergent to y bar. Clear? So this is yk bar weakly convergent to y bar, and yn is weakly convergent to y. So it is a subsequence of this. If it converge to some point, then it converge to a unique point. Then it means yk bar subsequence, it is a subsequence of yn. If it converges to unique point, by uniqueness, these two members are equal by uniqueness of limit. By uniqueness of limit, because it is a subsequence of this, right? So its subsequence converge to y, also converge to y bar. So by uniqueness of limit, these are equal. If these are equal, then it implies yk bar minus y approaches to 0 as k approaches to infinity. It means by substituting these values, so which is contradiction by 3. So this is contradiction by this result 3, because it does not approach us to 0, it is greater than 0, it is greater than epsilon. So which is contradiction, hence our supposition is wrong. If our supposition is wrong, then yn is strongly convergent to y. Clear? So under that, basically compact operator convert the image of compact operator convert weakly convergent to strongly convergent. Now next theorem is show that a linear operator T, linear operator means linear transformation T from n to n dash is compact if and only if image of unit ball M is relative compact in n dash where n and n dash are non-linear space. So basically it is directly we can find it from the definition. Now T is from n to n dash compact linear operator, that is given. What is our purpose? We take a unit ball M, right? And its image Tm. So this is a unit ball in n. So clearly M is bounded. T is a compact operator and M is bounded set in n. Then its image in n dash is relatively compact. That is by definition of compact linear operator. So that is our first part. Now second part. Given T of M is a relative compact for every unit ball M, which is M unit ball in N. Right? Now let S be a bounded subset of N. In order to prove compact operator, we take a bounded set in N, then its image should be a relative compact. So we take bounded set of N. If S is bounded subset of N, then S can be written as for every x belongs to N, such that norm of x less than equal to C, where C is some positive constant. Clear? Now, comparing these two results, from this result, it is a unit sphere with origin 0 and radius 1. It is a unit sphere of origin 0 and radius C. So, the relation between them is S is equal to Cm. That is relation, Cm. Now, T of S can be written as a T of Cm. Since T is a linear operator, so C can be taken outside because it is scalar values. So this is T of M, right? Or T of M is relatively compact. That is given. If it is relatively compact, then it implies its closure is compact. If we multiply by C, then again that is compact. So what is that? It implies closure of T of Cm is compact, right? If this is compact, then what you mean by this? It means closure of Ts is compact. It implies T of S is relatively compact, and it implies T from N to N dash is compact operator, right? So this is our result. Now next result is again, if T from X to Y is a continuous mapping of metric space X into metric space Y. So this is X, this is Y. So T is a continuous mapping. Show that image of a relative compact set A is a relative compact, right? So basically continuous image of continuous image of relative compact is compact. So that is the statement of this theorem. In order to prove this, I take A, which is relatively compact in the X. My purpose is its image T of A is relatively compact. Now, if A is relatively compact, then its closure is compact. Clear? And in the basic topology of Walter Rudin, in the first semester, we read that the continuous image of compact set is compact. The continuous image of compact set is compact. Now, what is A closure? A closure is compact. What is T? T is continuous. So its image T of A closure is compact, right? This can be written in this form. So TA closure is compact. Then it means T of A is relatively compact. If T of A is relatively compact, then it means E of A is relatively compact. Then it means continuous image of relatively compact set is again a relatively compact, right? So this is very important result. Now, after that result, there is a definition of epsilon net, right? So that we will discuss in the next lecture.